So, very good morning. Welcome to this session and the course on steam and gas power engineering. Today discussion on regenerative Rankine cycle. Okay, so the performance calculations of regenerative Rankine cycle and efficiency relations of regenerative Rankine cycle, and what is the comparison between ideal and reheating and superheating and regenerative Rankine cycle. These are the efficiency, thermal efficiency improving methods of Rankine cycle. So this session today agenda is that regenerative Rankine cycle and efficiency calculations. Okay, now mm, this is yes, this is the typical uh, steam power plant cycle. Okay, of regenerative system. This is the typical power plant recycle. So here, just you recall in previous lectures, we are discussed that superheating condition. This is also one efficiency improving method. So that two condition, you maintained constant pressure and temperature is increased. It is saturation to superheating condition, and sometimes so you increase that pressure. So sorry, at pressure heat supplied is continuously increased. Temperature is increased at constant pressure, and you increasing pressure, boiler pressure, then definitely temperature is also slightly increased. So you find that data in previous lecture. Similarly, in reheating method, you are introduced to two turbines. One is high pressure turbine and other one is low pressure turbine. Okay, that high pressure turbine is so yeah, I think yes, high pressure turbine and low pressure turbines. So based on that reheating method, you are observed that efficiency and improving methods, efficiency improving method and work output. Okay, and similarly in ideal Rankine cycle, that ideal Rankine cycle have involved four processes. Based on the four processes, you derived that equations, efficiency and performance equations. This is a reheating method. So high pressure turbine, low pressure turbine, and this is high pressure turbine and low pressure turbine generator and steam generator and boiler, condenser and pump. Again, after turbine work, again it is connected to steam generator. Then reheating process, temperature is increased and pressure is also increased. That high pressure and high temperature again entering to the low temperature, low pressure turbines. This is a reheating process. And then that normal or ideal Rankine cycle have involved four processes: compression and expansion. Then this is a pump work and turbine work, heat supplied and heat rejection. Based on the processes, you can you derived that equation efficiency is equal to F network and divided by heat supplied H3 minus H4 minus H2 minus H1 divided by H3 minus H2. These are the typical relations involved in ideal Rankine cycle and superheating condition. This is superheating cycle. Okay, you are increasing that PV area of the diagram, then definitely performance is increased. Okay, the temperature is also slightly increased from 3 to 3 dash. This is isentropic expansion. This is isentropic compression, pump work and turbine work. Based on this cycle, you are already derived that equations. This is superheating. This is ideal and reheating methods. So today's session is mainly focused on the uh, regenerative methods. In this regenerative method, you are additionally introduced two devices. One is second pump. This is pump one. The two pumps especially in regenerative process. And one more additional device is feed water heater. Okay, what is the function of feed water heater? Extracting heat from steam turbine, or bleeding heat from steam turbine. That steam could have produced more work by expanding further in the turbine that is used to heat in the feed water heater. That means that extracted steam from the turbine entering into the feed water heater, and after pump work that high pressure liquid is again entering into the feed water. Both that high pressure water and extracted steam mixing in feed water heater or mixing chamber. Okay, so then that mixture is again entering to the pump 2, that pump 2 increasing some pressure, so that inlet values of boiler is very high, maybe pump temperature or pressure. So that high pressure and high temperature, so that high pressure liquid entering into the boiler, then with the help of some heat, then that boiler is converted, that liquid is converted into the steam. So what is the main advantage of this regenerative method, or for feed water heater? Okay, here one major advantage is efficiency improving, thermal efficiency improving from 2% to 5% around. Okay, this is one major modification and major advantage in this regenerative method. And other uh, advantage is it controls mass flow rates. It controls the mass flow rates of steam turbine, final stages of steam turbine. Okay, it controls the mass flow rates of the steam at the final stage of steam turbine. So here one other advantage is you reducing that heat supplied at constant pressure process, because that inlet of the boiler is and inlet condition of the boiler is more pressure liquid. So you that pressure is more, automatically reducing that input heat supplied, whether it is heat supplied or pump work. There is no need to additional pump work here. This is one another advantage in regenerative method. And finally, and one more advantage here, you reducing the rejection of steam from steam turbine. Okay, regenerative method, especially in this regenerative method, you have several exiting points, or several extracting points, and several bleeding points in steam from the steam generator. See, look at this diagram here. At point 5, is high pressure steam and high temperature steam entering into the steam turbine. That point 5 to point 6, this is one process. Then after turbine work, then isentropically expanded, so that steam again entering to the feed water heater, then remaining steam is entering to the condenser. Just I can compare with numerical values. For example, if you send at 100 percentage of steam into the steam turbine, that 40 percentage of steam is converted to work. So that 40 percentage of steam is converted to work, that is 40 percentage is work done by the system. Then remaining 60%, out of 60%, 30% is again connected with feed water heater. So that 30 percentage, you are improving that 30 percentage of heat steam rejection in this method. Remaining 30% maybe it directly connected with condenser. Then after condensation, it will be changed, that phase will be changed from steam plus liquid, it is changed into the liquid. So this is two phase region, this is single phase region. Then that low pressure liquid entering into the pump 1, then definitely some pressure is increased. That high pressure liquid and this extracting steam from the steam turbine, both are mixed in the feed water heater. Then after heating process, then that steam and the liquid is entering into the pump 2, and again temperature and pressure is increased. That steam and liquid is entering into the uh, boiler. But ideal Rankine cycle, that complete steam entering, complete liquid entering into the boiler. But here, at least 70% of liquid, remaining 30% is steam. So it is the possibility to improving the thermal efficiency of Rankine cycle. But in practical scenario, how difficult, different issues you are introduced in this particular cycle. Okay, now I just want to go through this complete cycle. I can give you that a brief introduction about this. So initially that high pressure steam entering into the turbine. So the turbine work is from process 5 to process 7. Intermediate process is 6. So the turbine work is 5 to 6 and 6 to 7. Okay. Then after extracting steam from the steam turbine, that is entering into the feed water heater here. Okay, that liquid plus steam both are combined in feed water heater. Automatically that is converted to at least 40 percentage of steam, and remaining 60 percentage is liquid. Okay, that combination entering into the pressure pump 2, again pressure is increased. Okay, then that 40 percentage have chances that 40 percentage improving to from 40 to 45. That 45 percentage is steam, remaining 55 percentage is water. That combination is entering into the boiler. That the boiler is converted to that remaining 55 percentage of steam into liquid into steam. Okay, this is one typical process involved in that regenerative or regeneration method. So that this process is called regenerative process. This device is called as a regenerator. This device is called as regenerator. Sometimes it is also called as single stage feed water heater Rankine cycle. Okay, sometimes this is also called as single stage feed water heater. Okay, you introduce a number of feed water heaters, so multi-stage or so on. Okay, so this is a brief description about regenerative Rankine cycle. Now we'll come on this, what is Y and what is 1 minus Y. How much amount of steam extracted from steam turbine at point 6? So I can imaginary that value is some steam, that steam is called Y. Then remaining steam extracted from the turbine, that will be connected into the condenser. That steam is 1 minus Y. 1 minus Y. So this is Y, this is 1 minus Y. Okay. So based on this cycle, I can draw the TS diagram. This is TS diagram. Process 1 to 2 and 2 to 3. These are the two pumps involved here, and 3 to 4. Okay, up to 4. This is boiler inlet condition. This is turbine inlet condition. This is constant pressure process, heat supplied and isentropically expanded from point 5 to point 7. That is state 5 to state 7. That isentropically expanded means turbine work. The turbine work at 5 to 6 and 6 to 7. Okay. Then 7 to 1 is heat rejection. 7 to 1 is heat rejection. Okay. Now we will try to derive these equations based on these relations. We'll try to derive that equation based on these relations. Yes. So this is This Y is called uh, 1 kg of steam leaving the boiler, expanded partially in the turbine, and it is extracted at state 6. That is steam extracted. How much amount of steam extracted at state 6 are leaving or bleeding that steam at state 6. So I can write that steam is Y, and the remaining steam, that remaining steam is entering into the condenser, so that steam is called as 1 minus Y. If you considering mass flow rates, that mass flow rate through the boiler, I called that mass flow rate is m dot. So 1 minus m, that is extracted heat or completely extracted heat at zero point 0.7 or state 7 before entering to the condenser into mass flow rate. Into mass flow rate. This is the mass flow rate through the boiler. Then finally, these are the typical equations involved and performance calculations involved in regenerative Rankine cycle. So this is heat supplied Q1. Okay, heat supplied Q1. That means process 5 to uh, 4 to 5, and heat rejection takes place process 7 to 1, and turbine work and pump work. Just this is a diagram. This is turbine work, this is heat supply, this is pump work. Based on this, I can write that equations in terms of enthalpies. Okay, so that heat supplied Q1 or heat supplied Q1 or Qin is equal to H5 minus H4. Heat rejection Qout is equal to H7 minus H1. Okay, you don't bother about that 1 minus 1 and Y. Okay, that 1 minus Y means amount of steam extracted at particular point. At particular point means state 7. That Y means amount of steam extracted from steam turbine at state 6. Okay, you have any difficult, you feel any difficult in these equations, you can simply remove that 1 minus Y and Y. Okay, no problem. So that H5 minus H4 is heat supplied, heat rejection is H7 minus H1. Similarly, the turbine work is H5 minus H6 plus H6 minus H7. At where itself that 1 minus Y steam is rejected from steam turbine at state 7, that's why I multiplied 1 minus Y. Okay. Similarly, finally I can write this equation H5 minus H6 plus 1 minus Y into H6 minus H7. Okay. I clearly mentioned that closed cycle. So this is 1 minus Y, amount of steam is extracted at state 7, and Y is steam extracted at state 6. Based on this, I can write that equations. Based on this, I can write that equation. Boiler, turbine, again feed water heater, pump 2 and pump 1 and condenser. Here steam extracted, that is called as Y. Here steam is also extracted, that is called as 1 minus Y. Okay. Now this is pump work 1 minus Y into, here two pumps involved in this regenerative Rankine cycle, pump 1 plus pump 2. Here pump 1 is in between that 7 to 1, so I multiplied 1 minus Y, that percentage of steam extracted at state 7, plus pump 2 work. This is pump 2 work. So pump, yeah, you are already seen in yesterday problem. If any equation you do two unknowns, it is impossible to find that known values. Required values. So that pump work I can write in terms of volume into pressures. That is, these volumes are specific volumes. Those values taken from steam tables. So pump work in first pump work is V1 into P2 minus P1, and second pump work WP in is V3 into P4 minus P3. Okay, now I know that pump work and I know turbine work, so I can find net work done. So the net work done is equal to turbine work minus pump work. So H5 minus H6 plus 1 minus Y into H6 minus H7. This is turbine work. Then pump work is, this is pump work. So that 1 minus y, v1 into p2 minus p1 plus v3 into p4 minus v3. Okay. You have any difficult in this equation, you try to remove this 1 minus y, here also 1 minus y. Simply you can write h5 minus h6 plus h6 minus h7 minus v1 into p2 minus p1 plus v3 into p4 minus p3. This is the net work done. Then net work done divided by heat supplied. Efficiency is equal to net work done divided by heat supplied. So that heat supplied is where itself heat supplied at Rankine cycle. Rankine cycle heat supplied is, this is Rankine cycle. Heat supplied is at a constant pressure process from 4 to 5. This is heat supplied here. Okay, so I can write that heat supplied equation in terms of enthalpy. So H5 minus H4. This is the final formula, net work done divided by heat supplied. Okay, I can stop here in today's lecture. Tomorrow we will discuss, we will do that examples, worked examples of Rankine cycle and reheating Rankine cycle and regenerative Rankine cycle. Okay, thank you.